Hi, it's Terry Dennery of the MathWorks. So in this video, we're going to continue, and this one I'm calling selecting components that get the job done. And so what's the job? Well, you know, um, that's a pretty loose definition, but ultimately it's making sure the machine does what you want it to do and handles the various missions that you need it to handle. So anyways, we'll get into a loose definition of what we might mean by that as we proceed through this. Right. Now, the other thing I want to begin with, well, actually, the thing I do want to begin with is let's look at where we left off, which is we've established these very useful parameters for defining what the motor is. Stall torque and no load speed are very useful, and that they reflect what you're going to ask it to do. All right. And so, anyways, for right now, for what this shaft is, I'm not exactly sure, what that might mean. I think I might put it back in at 1 Newton meter, and according to how I want it to move, that 1 Newton, not 1 Newton meter, but 1 kilogram meter squared, that's gonna have a big impact. So, anyways, there's a lot of stuff here, and even though it's a simple mechanical model, that are gonna dictate kind of what motor we should use for the movement that we want. Okay, and so what I want to begin with on this one is we're going to create another block. And so this one, I'm going to use this and its parameterization to some advantage just to be kind of efficient in doing this. But I'm going to begin by changing the name. I'm going to call it inverse mechanical shaft, right? And the basic idea of this is I want the output not to be shaft velocity, but I want it to be torque. So I'll begin by labeling an output T, and I want its input to be W, or at least I want it to be the motion of the shaft. All right, and so now I want to kind of figure out what that means. And so it's going to mean that I'm going to accelerate at inertia and I'm going to deal with damping. And so as soon as I kind of start thinking about, well, I know I want it to be more than just W. And so I'm going to change the input to motion. And PVA is a designation I use quite a bit. And I think it's very appropriate, but certainly isn't kind of standardized or conventional yet. So I'm going to add a little bit more. And so I'm going to just put rad comma S, indicating that it'll be defined in radians per second. Oops. Now the other thing I want to do is introduce a demux, because what PVA ultimately means is a three-component signal, right? And the components will be P, position, V, velocity, and A, acceleration. And if you have a motion profile with regard to time, clearly those are all kind of constrained within each other, but again, you need to be very kind of attentive and specific and make sure that you do that properly. And so anyways, let's kind of set it up so that we will be working with those three components. All right. All right. And I'll begin with the damping. All right. And it's P at the top, V in the middle, and A at the bottom. And so certainly a component of the required torque will be to deal with the damping. And then the other component will have to do with J, right? And so instead of it being 1 over J, it'll just be J, the inertia. Okay. It's simple enough, right? And I think I'll just terminate the position because the position is not going to be directly used to kind of estimate the requirements of this motor based on the mechanical model. And so it's simply just adding these two. I'll bring in an add block. Got them the right size in the first try, right? And let's set this up. Let's look at the whole thing, and I'll delete all this stuff that was in there before. And then I'll do one more thing, which is set the units on the output to be Newton meters. Okay, and with that, I kind of got what I want, right? And so it's looking for a trajectory. Now, the other thing I need to kind of go and consider now is how do I want it to move, right? And so just kind of a quick story is, when I first joined MathWorks, that I really didn't know that much about controls, so I was learning quite a bit about controls. And I met all these controls engineers who were saying, well, I'm going to just ask for a step response. And I'm like, step? I'm a mechanical engineer. That's impossible. That's an impossible request. And it's kind of the amazing thing about controls is that you can kind of deal with amazing or impossible requests, and that there's very, I'll say, great interpretation that takes place in how well control algorithms work. Okay, but I'd still say that I'll have the bias towards wanting intention to be a big part of how we do things. And so what we're going to do is we're going to use these blocks that I created. You can see that they're in my own personal library right there for defining kind of, good valid transitions. And so we're going to be very specific. I'm going to say, I want you to go from 0. We're going to do, again, one rotation. So it'll be in radians. So it'll be 0 to 2 pi. And let's do it in 3 seconds. All right. And let's just kind of look at what we got. Actually, I think I'll use the same demux block so that we can kind of look at this. And send that in right there. And we will create a scope that's of the same height as this. Unfortunately, it's kind of going off screen, the arrangement, but I'm just matching, oops, the scope at the same height. All right. Please excuse my awkwardness as I set this up. So we're going to look at all 3 components. All right, and let's hit run. Oops. Not looking at torque, but we're looking at the input, which is right there. And we will lay this out with 3 separate scopes and make it as big as possible, but we'll see that transition from 0 to 2 pi. And I think if you kind of study this closely enough, you'll basically see that that the second curve is the first derivative of the first one, and the third curve is the first derivative of the second. So essentially position, velocity, and acceleration. Right? And so with that very intentional specification, now we can look at torque. And we'll hit run. And that would be the torque for this shaft required to achieve the motion that we just selected. All right. And so there's a little bit of work to be done still before we understand how to adjust the voltage, and it will be done with controls, including feedback controls, to achieve the torque that we want to achieve. Right? And so just to kind of validate it, I'll send this value in, and I think we'll just kind of be happy to see that that we're going to get the velocity that we saw in the previous curve. All right, and so we're seeing a velocity right there. It's like 3.5. I'm going to make sure it's consistent with this one, which it is. 3.5 radians per second, and a torque of 3.5 Newton meters. Right, and based on my motor, I'm pretty sure that we're going to be able to do that. But it will come down to how do we design the control so that we're adjusting the voltage to achieve that torque and therefore achieve the motion that we want to see from the system. All right, thank you.